Hello, guys. Starting this broadcast. Since we have 0 viewers right now, I'm talking to myself. Um, I'm waiting someone to join before we start our conversation. Okay, now that we have at least 1 viewer, I can start the presentation. So today we're gonna talk about some essential algorithms. And I've selected 5 algorithms to talk about. It may seem daring to talk about those 5 algorithms during half an hour, but let's try and see how it goes. So beginning with my notes here. The first algorithm, and this is the 5 algorithms we plan to cover today. The Great Common Divisor is actually the oldest algorithm that we know about. The binary search, merge sort, hashing, and Dijkstra algorithm. That's the hardest one. You barely cover the Dijkstra algorithm, but we try to go a little bit into it. So next one, let's see the Great Common Divisor. This algorithm has been developed 13 before Christ, so 300 before Christ actually, by Euclid. And the idea is to find the greatest integer that divides both two numbers. As far as we know, it's the oldest numerical algorithm that's still in use, and it has been described in the work Elements. This is a fragment of the work Elements. That's the Greek translation, in case Ves is watching. So this is the algorithm, plain and simple. We can describe it as a recursive algorithm where we call the function itself. So inside the function, we call the function. So that's the recursion step. And we have to return the recursion in case v is different from 0, and return u in case v equals 0. That's the greatest common divisor. Show an example to make it clear. A little bit longer. And then we have this example. If I want to calculate the great common divisor between 90 and 86, I'll have my first step, the GCD, I'll call the function GCD 86, that's V, and 4, that's 9, is the remainder of the division of 9 for 86. So I'm calling GCD 86 4, and GCD 86 4 will call GCD 4 2 because it takes V, it's 4, and 2 is the remainder of the division of 86 per 4. And then we call GCD 2 0, and we get the result 2, because when V equals 0, we are returning the U, that's 2. So that's pretty easy and pretty clever, this algorithm, and one of the most basic algorithms in computer science. It's used mostly in factorization. If you want to break the RSA code, the cryptography, the asymmetric cryptography, you need to find a quick factorization. This algorithm, as strange as it may sound, it's pretty efficient for some quick factorization. It's not the best factorization algorithm, of course, but it's pretty effective. So we covered the great common divisor, and now we are going to move to our next step. That's the binary search. Binary search is as we saw last time, is the fastest search available for us. The fastest search in the West. It's an algorithm that we saw last time that has the complexity that is the logarithm of the number of entries. It requires that you have a sorted list to work, and very easy to implement. So let's give an example of how it works. Let's suppose we want to find in this list, where is Ruslan? Since Ruslan is watching probably, I think at least he shows up in my list here. I'm asking for the list, where is Ruslan? And I ask Justin, Justin, where is Ruslan? And Justin answers, he's below me. So I look below and I go to Soto, that's in the beach, and say, Soto, where is Ruslan? And he says, it's above me. And I go to myself and ask, where is Ruslan? And I say, below. And oops, this presentation is always tricky. Just clicking. And I ask myself, where is Ruslan? And it points to me. So one second, please. Next, sorry for the interruption. Next, we see the implementation of the binary search. So the binary search is pretty straightforward to implement. We have a high and a low value, and we do this in a recursive way. using the function binary search, calling it 2 times inside the function binary search. So it's a recursive algorithm also. Next in our list, we are going relatively quick in this list because we have lots of ground to cover, and this is probably the algorithm that will take more time for us to explain, is the merge sort. We discussed it before. The merge sort is one of the fastest algorithms, and in terms of sorting, it sorts in logarithm time versus the size of the list, so n log n. And it uses an interesting strategy that's divide and conquer. That strategy is used on computer science on several occasions, and we are using this to demonstrate how we can implement a very clever algorithm using this divide and conquer. So the idea is to split the list to the smallest form. The smallest form of a list is a list that contains only one element, and the list that contains only one element is, of course, sorted. And we sort this list that contains only one element, that's a trivial sort, and then we go to the merge step. So we are spending our time mostly on the merge step. So to give an example, we have this list, 85, 24, 63, 45, 17, 31, 96, and 50. And then we are going to divide the list in the first sublist, divide again, and divide again. And now we have a sorted list that contains only one element, that's 85. And then we are going to go to the next step of the tree and take the 24, it's sorted again, and we have this, and we merge this. We merge the two elements that have been sorted, that is 85 and 24, and we get this 2485. So we can do this for the next element of our tree, 6345, and we go to 63, and then we sort this 45, merge this, go up, merge this, and now we have this branch of the tree merged and sorted. And we go up, and then we move to the next side, and I won't show every step because it will be boring, but we are having this the same way, and it's sorted. And now we have the last step that merge the two halves of the list, and this gives us the sorted list. So most of the work is done on the merge step. And the merge step is very straightforward to make. You have the two lists, and you take a pointer to the first element. Oops. You have a pointer to the first element, and then to the second element, and you go moving, comparing those elements to see which one is the smallest one. So now I have 45 and 33. I compare 3, then I choose 33. I take 33 and move forward to 42. I compare 42 with 45. I take 42, and I compare 45 with 67. I take 45, and I compare 98 with 67. I take 67, and now I only have 98, and I finished merging my lists. So that's the merge sort. We check if our list has only one element and it's sorted. Otherwise, we call merge sort to the two sublists we have, and then we use the merge step. The merge step is the most complicated step on the algorithm, but very straightforward. So that's the divide, and that's the conquer. So we are using this approach in really dividing and conquering what we divided. That's my pointer. It's complicated. So that's the merge step. The merge steps basically does what we showed on the the previous slides. Well, next we're going to talk a little bit about hashing. And so what I'm saying that there's a lag. I don't have feedback from you guys otherwise. So I'm not sure who's listening, who is not listening. This Hangouts is kind of, it seems to have a group chat on your right hand, but no one typed it on the group chat, so I have no idea who's watching and who's not watching anymore. But let's continue. It's always recorded also, so if anyone wants to watch again or another parts, it will be recorded and there will be no lags on the recording. So for hashing, we now want to see this interesting thing that's called hashing. Hashing is a process where you use a function to take an entry and separate those entries on buckets to give a number for each entry. For instance, in the United States, the Social Security number is a hash function that gives a unique number for each citizen. So sorry guys, I can't answer the on HipChat right now, but I am sure that the video is streaming to everyone. I try to reset the presentation. Not sure if you are watching. I'm not sure if it's your connection or maybe it's something with G+. Are you seeing? Yeah, it's confusing today. Alicia is watching the screen share, I think. Not sure who's watching. It's kind of messy today. I'm sorry, guys. Yeah, but it seems Adam is complaining that he cannot load, but at least Alicia is watching. So it stopped on a merge. So probably something with your connection. I'm not sure if Alicia is seeing the hash function because I don't have any kind of feedback from the viewers. Maybe we need to find another way to make those presentations, otherwise it will be complicated. But since it's being recorded, I'll try to keep talking until we finish, because I promised to finish by 11:30. So the hash function, it's a function that takes an input and gives a unique, ideally an unique output. Hash tables are used for hashes are used for hash tables. That's a pretty, you're seeing the box but not the functions. That's weird. Adam's watching. Alicia is seeing the, let me check. Okay. So Alicia is fine now. So let's try to resume our presentation. And where is my screen? Now I lost my screen. Oh, here you are. Okay, so hashes are used for hash tables. That's a pretty efficient way to find an element on a table. It's used also for authentication, for cryptography. Of course, we use this on our evolve system. We use hashes every time. It can be used to find duplicate files, and of course, it's interesting usages, Bitcoin and other cryptographic currencies like Littlecoin, etc. So let's talk a little bit about hashing. As hash tables, our idea is to find elements on average using only one query. We discussed that the binary search has order of logarithm of the number of inputs. But what if we could have a function that, on the worst case, would take a full scan on the table, but on the best case, would take only one step to find the buckets, to find the key we are searching on our database. So that's what hash tables are. They are interesting structures that, if well implemented, on most cases, will give you a faster answer than the binary search. The binary search is guaranteed to be the fastest search on all circumstances, but hash tables can be faster than binary search under some conditions. So they are very interesting structures to learn. And the next step is authentication. We have authentication, for instance, to not store user passwords on our server. It's ideal that we should not store passwords on our server, because storing passwords on the server is a bad practice. We have a breach of security, as some companies had on the past. LinkedIn had a breach of security that exposed literally millions of passwords, and other companies had breach of securities. Recently, it seems that this website, Ashley Madison, had a breach, a huge breach of security that exposed passwords and user information. So hashes is an interesting way to store a password in a way that's non-recoverable. You can test if the user entered the right password, because you're passing through a function and comparing the output, and the output should be the same, but it's impossible to generate a password back from the output. So that's the cryptographic hashes. You can see that if you make a small modification on your inputs, you have a completely different output. That's called the avalanche effect on the cryptographic functions. So good cryptographic hashes like MD5. MD5 is actually outdated now, because there are some attacks that have been discovered on MD5 that make it's now unsuitable for most cryptographic applications. But SHA 256 is a good function for cryptographic hashes. and it generates different results for every input it receives. So the base for a good cryptographic hash is easy to generate, virtually impossible to revert. If you have an hx, you cannot derive x back. That's the assumption we have, and virtually without any collision. So you cannot find any two entries that pass through the hash function will have the same result. Of course, if you have an infinite number of tests, you can have a collision, but that's the word virtually is for, to say that even a reasonable and human computable or given our current resources, it's virtually impossible to find any collision, so you cannot fake a password. And to analyze this stuff with collision, we talk about an interesting problem that's called the birthday paradox. The birthday paradox is an interesting paradox. I don't know why it printed everything, but given n people in a group, what's the probability that two of them have the same birthday? If you take, for instance, one person and ask what's the probability that other one person will have the birthday on the same day as me, and that probability is 1/365. But if you have 10 people, the probability goes to 11%, and that's an incredible result because it doesn't seem natural. If you have 20 people, you have a probability of 41%, and if you have 23, you are going over 50%. So with the number of people we have at Cypher Health, we have more than 95%, 97% probability that the two people have birthday on the same day. So if you ask the blue team about all the birthdays, I can bet with any of you that we have two people that have the same birthday on Cypher Health. So that's the calculations. I'll spare the calculations, but the calculations are on the presentations in case anyone wants to go a little bit deeper on the subject. We have this number 365 factorial over 365 at n times 365 minus n factorial. That's the probability given a number n for the birthday. But let's suppose that we have a year that has not 365 days, but instead has 1,000 days, 1,000,000 days. How our probabilities will behave? So that's the generalized birthday paradox, and that's used to attack cryptographic function, because you need actually this quantity of attempts, that's the square root of the possibilities of your hash function times 1.17 to have a 50% chance of hitting twice the same function. So if you have a function that generates a small number of possibilities, no matter how well you have this function designed, it's easy to design an attack that finds a collision and it breaks the assumptions of a good cryptographic hash. So that's the generalized birthday paradox, and it's easy to implement a Python script or a Ruby script. You can do this just for understanding the process, and the script takes a random day and samples this 10,000 times for finding any people that have birthdays from 1 to 365 person. You see that the probability goes exponential up to close to 100%. So that's quick. The probability goes very quick to 100%. That's the birthday paradox. So and finally, we have to talk a little bit about the Dijkstra algorithm. I think the pronunciation, he's a Dutch, so the pronunciation, it seems to be like something like Dijkstra, or but we need to check with a Dutch man or Dutch woman to see how the pronunciation goes for his name. But Dijkstra was a computer science for Netherlands, and he designed it in the 50s an interesting algorithm called the Dijkstra algorithm. That's the idea is to find the shortest path between two nodes in a graph. There are several uses for these algorithms, a number of uses. This algorithm is more used than we can imagine. Some applications is to find the best route from the office to the Empire State Building, mapping, routing, like Waze, Google Maps, you name it. Find a solution for Rubik Cubic. For instance, you can find the solution using this algorithm, or find the degrees of separation between two actors. If you go to this website, oracleofbacon.org, it's a very interesting website that shows you give two actors, two Hollywood or no Hollywood, Bollywood, whatever you want, where Russian actors, Indian actors, Iranian actors, and you find the degrees of separation between those two actors, and it uses the Dijkstra algorithm to calculate it. So it's very interesting, and we have only this overview of the Dijkstra algorithm. So as we finish, we go to our recommended readings, if anyone is interested in learning a little bit more. The first reading is a very interesting blog post from Google research showing that most implementations, although the binary search and merge search are very easy to implement, most of the implementations we find in students and some non-mainstream libraries are broken. It shows why. There's this sorting algorithms demo that compares several algorithms. There's this visualization of how the Dijkstra algorithm works, and a quick explanation, 3 minutes, of how the Dijkstra algorithm works in this nice YouTube video. So to finish, as always, we have this exercise to solve for, if anyone is interested in this site, HackerRank is very, I think the pronunciation is HackerRank, and it's to implement the Dijkstra algorithm and compare with other people to see how you perform in terms of timing and optimization. And if you, I can assure you, if you implement the Dijkstra algorithm, you can say that you are now a grown-up programmer. So that's the idea behind this talk, to show the 5 most essential algorithms. I think it would be interesting to implement each of them at least once in your lifetime. And next week, hopefully, we have a better connection and a better transmission through Hangouts, or you find out another way to make those presentations in a better way. So thank you very much, and see you in 2 weeks.